Hello, everyone, and a warm welcome to our Fellows Public Talk series. I'm Claudia Rizzini, Executive Director of the Fellowship Program at the Harvard Radcliffe Institute. It is my pleasure to introduce Ralf Klessen, our Elizabeth S. and Richard M. Cashin Fellow. 4.5 billion years ago, a swirling cloud of gas and dust, propelled by waves of energy and drawn together by gravity, laid the foundation of our solar system. At the center of this cosmic cloud, a star slowly took shape over millions of years, giving rise to the sun. Ralf's research focuses on how stars like our sun form amidst the cold, turbulent gas and dust that permeate the Milky Way. Stars are often praised for the beauty of their milky glow, illuminating the night sky. Yet, their formation plays a much more fundamental role in the universe's evolution. Ralf uses numerical methods to model how star formation gave way to gravitational waves, supernovas, and planets like the Earth. Looking to early universes and our contemporary galaxy, Ralf's models have demonstrated the new dynamic relationship between interstellar gas, turbulence, and star formation. His research has contributed to astronomers' effort to chronicle our galactic origin and our solar system's place within the larger galaxy. Like any ecosystem, the Milky Way is composed of various interrelated environments. While at Radcliffe, Ralf is developing computer simulations to create 3D models of the sun and its surrounding environment, known as the local bubble. Using the abundance of existing astronomical data, Ralf's simulations will begin to untangle the complexity of the processes that shape the local bubble and its role in the larger galactic ecosystem. The Q&A portion of the public talk today will be moderated by Alyssa Goodman, Radcliffe Fellow in 2016 and 17, and Professor of Applied Astronomy at Harvard University. And now please join me in welcoming Ralf Klessen to the podium.
All right. Thanks, Claudia, for this very nice introduction. I want to invite you today to follow me on a journey into our galactic neighborhood. The question is, what's around the corner, and why should we care? So the question is, how can we understand the place in the Milky Way? And the journey I would like to follow me today is split into several parts. I start with an interesting question, which you may not potentially expect from an astronomer. I have two prolegomena which try to explain something about the scientific process that we follow as astronomers and astrophysicists. I think it makes sense to talk a bit about the scales we usually deal with in astronomy and astrophysics, because often they're very remote to our everyday scales. So it makes sense to get a feeling of what is the scale and the size of celestial bodies. And then I ask the question that came up in the introduction, what's around the corner, and then I try to wrap up. So before I start, let me say thanks, not just for this very kind introduction, but also to many people and institutions that allowed me to be here. First, of course, to the Radcliffe Institute of Advanced Studies and for the very helpful, very supportive staff. So many thanks. This is really greatly appreciated, what you do for not just me, but all our fellowship people. Of course, thanks to the fellows for many discussions we had, stimulating things, new thoughts that I quite learned from a very diverse crowd. I usually do not speak with journalists or poets, rather with my own crowd, and I must say I learned a lot. And of course, I'm also, while being here, affiliated with the Harvard Smithsonian Center for Astrophysics, Elisa Goodman is part of it. I see a few other colleagues here. So many thanks also for your friendship and for supporting me and for cool scientific discussions. I think I need to really thank most the crowd on this slide, the many postdocs and PhD students that have been part of the group in Heidelberg over the years. And usually when you're a PhD student, you think, oh, there's so much you can learn from your advisors, from your kins and from your elders. But this is not true. I must say I've learned probably much more from my students than they from me, because they dig deeply into the field, into something that I have no time to really invest so much. So this is really helpful. And of course, I have to also give credit to the many, many collaborators across the globe that contributed to me being here in the end. All right, what's the starting point? So my starting point is the question of whether this guy, which, if you have not seen, sits in the Harvard Museum just around the corner, could produce this painting, which is not quite around the corner. It sits in MoMA in New York City. And if you look at Vincent van Gogh's oeuvre, he has painted the Starry Night in many different forms. So here's another one. This is the Starry Night over the Rhone Valley. And what is common to all of it is, I think, the awe of the author when looking at the night sky. And I think this is an awe and a source of inspiration that we all share. But there is a question, and the question is actually, what are the chances? Is this just, normal? Or are we living in a special time such that we actually do see stars on the night sky? And now it becomes a proper astronomical question because, the Earth, or the Sun and with it the Earth, moves around in the galaxy. At the moment we are in a specific environment. We are in the local bubble. That was also in the first slide and in the title. And this is a bubble of very tenuous gas evacuated by a sequence of many supernova explosions that has shuffled away the interstellar medium to quite a degree. Density has dropped by a factor of 100 compared to what it should be at this part of the galaxy. So how does this influence the night sky? And as the Earth moves every 220 million years around the center of the Milky Way, how often does it encounter a similar environment? How often would it be embedded in a much denser environment, in a dark cloud that simply shades off the light of the surrounding stars? And you might think, why should we care? But if you look at this map, without stars on the night sky, this map would look very, very, very different. Why? Think of it. If you do transoceanic seafaring, you need the celestial bodies. You need the night sky to navigate. There are about 58 so-called navigational stars, the brightest stars on the sky. There's another 100 plus additional ones that we see in the navigational almanacs. And they have been used for centuries, millennia for navigation. So if you think of a world without Columbus, if you think of a world without Magellan, if you think of a world without colonies, the political structure would be vastly different. The Americas would be left to their own devices. Maybe the Mayans or the Incas would have expanded their territory. The major trade route would be the Silk Route connecting the Eurasian continent. What would have happened in Australia? So it also has other consequences. If there are no colonies, if there's no availability of easy to transport goods, cotton, from the colonies to the colonizers, there would be no industrial revolution in Europe. maybe we would not live in an age where, I can project it on the screen. I have here my laptop and this fancy device, which I can use to communicate across the globe with my daughter in Japan, for instance. So maybe our complete technical development would be maybe not stopped, but delayed. And because there are many artists, poets in the audience, what would be the consequences for, our spirituality? What would be the consequences for religion? So I would like to just mention these things. Maybe this triggers your thought and imagination. So coming back to the question, what are the chances that this might have happened, right? If there were no stars on the night sky in the past 2,000, 3,000 years, humanity would have developed very differently. So, do we live in a very special place? What is the likelihood of such an environment to occur as the sun and the earth travels on our wandering world through the Milky Way? So, what exactly is our cosmic neighborhood? And before I get to this point, let me come to my first prolegomenon. And let me go back about 2,000 and a bit years to this guy. So, imagine, Plato tells a story about Socrates. So these guys tend to, sit after an opulent meal and probably lots of wine together, and probably they feel a bit tired or dizzy. And so Socrates says, "Look, Glaucon, I will tell you a cool story. This make you awake again." So what is the story? Probably you have heard it many times. It's the cave allegory. And so imagine you are a poor cave dweller. You're sitting with your hands tied to your back on the wall inside a cave. And behind these walls are the puppeteers that hold up figures, and they are illuminated by fire, and what you see is the mere shadow on the wall of these figures. This would be your world. You would see dark and white, gray in between, two-dimensional figures moving on the wall. Now imagine that such a cave dweller just, unshackles its ties, and he climbs over the wall. And at first he would be blinded by the fire. But then he would see, there are three-dimensional objects, and there are real people, not just me, that carry these around. And so reality is not this two-dimensional shade, but these are three-dimensional things. And then he sees light at the end of a tunnel at the far distance. In the actual story, he's dragged out, but let's say he's a bit more inquiring in this story. So he moves out of the cave. He's again blinded, but for the first time he sees colors, flowers, butterflies, the sun, and he's absolutely stunned. He sees, wow, the world is so different to what in the cave I see. In Platon's case, the allegory is, this is the physical world, this is the mere shadows on the cave, and there's the spiritual world, the world of ideas. That is the real world. So the guy goes back into the cave because he says, I need to tell my fellow cave dwellers. And so he's blinded again because it's suddenly dark. Then he climbs over the wall and he tells his fellow guys, look, there are colors. There's three-dimensional things you have never even imagined. And they say, you're crazy, and they kill him. So if you think of it, that is very much the process that we have in astronomy. So our things may not be, what is this, a pig and an amphory, but something that is or qualifies as an astronomical object, in this case a molecular cloud out of which stars are forming. But the process is very much the same, because we never really see what enters our physical models. Density, mass, temperature. The only thing we can do is we can count photons, maybe neutrinos, maybe measure gravitational waves. And so there are, in addition, projection effects. There is all kind of physics to go from, the real world, what enters our physical models, and what we actually observe. And so in astronomy, what we do is we really try hard to close this loop, both from this side, the astronomical interpretation of data, but also from theory to make synthetic observables to really connect our models more closely to the physical world so that we can engage in a one-to-one comparison. And just in case you want to know, this is the sequence of events and equations and assumptions that need to be done to make a synthetic model of such a molecular cloud. If you were, in the field, you would immediately recognize, some of the assumptions are shaky. Some of the equations may not be the right one. Maybe you want to augment them by some terms. So this gives you a feeling that astronomical observations always can only give you indirect information. So whenever we look at data, we always need to come with a huge overbow of models, assumptions, interpretations. And I think this needs to be kept in mind. So that makes it difficult. It makes it up to interpretation. And of course, this gets more difficult the closer you are at the very frontiers of your field. Which leads me to my second foreword, to one of my favorite, more recent characters. He came up already once, I think, Li Xing. You mentioned a quote from Wittgenstein in one of your talks. I have to admit I could not resist in adding my favorite quote from Wittgenstein, from his Tractatus. He says, wovon man nicht sprechen kann, darüber muss man schweigen. So what we cannot speak about, we must pass over in silence. And what does he mean? So if he is right, I should stop my talk. Because I will talk about things that I cannot really talk about in the sense that this was meant. So what is the context of this quote? So in the Tractatus Logico-Philosophico, he essentially subscribes to a thought building that is called logical atomism. So the idea is that you can deconstruct reality into inseparable, smallest quanta of truth. And this works both for reality as well as, and this was his focus here, for language and the statements we make. So if we just split down our statements into these smallest quanta, into these logical atoms, they are truth and they are 100% fixed. Now, if you ever want to read a cool book, this is really nice. And he used it later for his PhD thesis in Cambridge, UK. And I must say, I wished my thesis would be so cool. Anyway, he completely changed his mind. And so much more interesting in the context of us are the philosophical investigations who came out posthumously in 1952. And here the statement is kind of everything is fuzzy. And the logical quanta do not exist, cannot exist per definition, clearly. And we all know that, right? When we communicate, this communication is always up to uncertainties, to fuzziness. So we need to agree about our terms. And so what do I mean? Let me ask the question, what do you see here? The biologist. 3 apples, very good. But how can you tell? How, 2 are round-shaped. but they have different colors. Two are ready to be eaten, the other one, has already gone through this process. Yet, we recognize this as being 3 apples, indeed. A KI head, so an artificial intelligence, would have great difficulties because there is fuzziness, there is interpretation. These objects share a large enough number of quantities so that in the common sense we agree to call them apples. But if you look at the details, there are enough qualifiers where they differ, color, shape, etc. But this goes deeper. So if I speak apple and you say apple, maybe you mean something very different because maybe you have fallen from an apple tree and you hate apples, or you are allergic, whereas I love apples and I have very positive resonances. So the words we use, even if they are obviously super well-defined, are up to interpretation, are up to fuzziness. And I think we need to also acknowledge that, maybe not just in the humanities and social sciences, but very much so also in the natural sciences. So if people tell you there is truth and there is a well-defined quantity, I think this is simply not true. If you go to the frontiers of science, the fuzziness becomes much more well-defined, much less well-defined and up to interpretation. I can look at certain astronomical observations. We have seen they have their own problems, but I come up with a completely different interpretation as my competitor does. And so we need to negotiate who is right, who is wrong. Most likely, and as time tells, we are both wrong to varying degrees. So I think that is an important message that you need to keep in mind. All right. Now, let me say a bit about the scales. And let me start with scales that you're very familiar with. And I have taken pictures from my hometown, so maybe you get some feeling of where we live and appreciate. So this is beautiful old town of Heidelberg. And as we have seen, there is, or as you see, there is a scale in meters, so in metric units, I'm sorry. I will keep metric units throughout this talk. Well, kind of. And you can see this meter is fuzzy because, an astronomical observation, if you get it right to a few percent precise, we are lucky. Often we talk about, factors of 2 or 3 or even more. So if we go up in scale, then the tower, which is about 25 meters, if we talk about orders of magnitude, order of magnitude is a decade larger, 10 meters. This is from the castle looking down onto the old city, and the Neckar is about 100 meters wide. And this is also, the span of the old bridge. We can go a bit further down and look from the hills surrounding Heidelberg onto the old city. And the valley is about 1 kilometer wide at this point. However, if we then enter into the Rhine plains, the city spills out into this plain, and it has a diameter of roughly 10 kilometers. So if we then measure units, this is the state of Baden-Württemberg, we have to go to 100 kilometers. And if we go to, scales that are of the order of our planet, we have to talk about 1,000 kilometers, which is a good scale to describe things in Europe. And we all know the diameter of Earth is something like 12,000 kilometers. So this is a good scale for our planet. Now, another thing I could not resist, this is probably the most iconic picture ever taken. This is the rise of Earth as taken by Apollo 8 on Christmas Eve in the year I was born. And the distance between the moon and Earth is 300,000 kilometers. So you see, we step up in decades, in orders of 10. Our home star, the Sun, has a diameter of 1.4 million kilometers. And just to give you an example of the size compared to the Sun, which does not even fit on this image. And this is just a standard protuberance, one of these plasma eruptions that the Sun produces all the time. These things are large, and we are tiny. If you go to the scales of the solar system, then these are the planets that we usually talk about, right? And Pluto is now a minor planet, but if we zoom further out, there is the Kuiper belt. This is where all the, many of the asteroids are, and eventually sometimes they kick each other and one gets kicked towards the inner parts of the solar system. And this is surrounded by an even larger entity, the Oort cloud. And now we get into distances where the next star is maybe, I don't know, a factor of 10 further away than this thing. So when we talk about star clusters, as you can tell, I have changed the units now to light years. So this is the beautiful image of the Pleiades. A star cluster may be 100 million years old. And from this, you can say it's about 10 light years across. This is our neighboring galaxy, Andromeda, and the light takes from one end to the other something like 150,000 years. So this is another fact about astronomy. If we look at distant objects, we are looking into the past. And this is why we can observe features of the early universe just by looking at the as far distant universe as possible. And these galaxies can interact. They can do a complex dance driven by gravity. And usually, as we have seen, things on Earth are clustered and structured. Also, galaxies do not evenly distribute themselves. They also come in groups and clusters and superclusters and so on. And so this is the local group of galaxies. We see the Milky Way, it's centered on the Milky Way. We see Andromeda here, and we have about 100 smaller galaxies, 200 by now, have been observed in the vicinity. This is a respectable galaxy cluster. It takes now 100 million years for the light to go across. And of course, then when we enter the scales of the universe at large, this is now, of course, images are hard to take. So this is from numerical simulations from colleagues in Heidelberg. We talk about, 1 billion light years. So this is roughly the scales. And just to wrap it all up and visualize, if you imagine the sun has the size of a grain of sand, so maybe 0.2 millimeters across, and there are about a few 100 billion stars in the Milky Way, which is roughly the same as there are grains of sand in a volleyball court, in a beach volleyball court. So if you want to keep the proportions, if you say each grain of sand represents a star, how far do you need to throw it out in order to reproduce the proportions of the Milky Way? Ideas. The astronomers should be silent. Who? 10 meters? Much more. What do the poets think? 1 kilometer, okay. No, to the moon. To the moon. You need to spread it out to the moon. So this tells you that space is exactly, well, mostly one thing. It's empty. And yet, we do have to worry about the gas that fills the space between the stars, because this is the key to answer the question I have formulated at the very beginning. So let me ask the question of what actually is around the corner. So what do we see when we pierce into the night sky. And of course, this is not what modern astronomy and astrophysics tells us. Before I get to that, let me very quickly say something about the projections. So when we talk about map making on Earth or map making on the sky, we have exactly the same problem because we are looking in the sky from the inside of a sphere out. And so we need to map a sphere onto a flat surface. And there are many ways to do that. The Mercator projection that is depicted here, you simply project everything onto a cylinder and then you see what happens. You see there's lots of distortions. You want a projection that kind of keeps the angles and the surfaces as faithful representations as possible. So what I show you and what is generally adopted is a thing called Mollweide projection, which is shown here. This is a Mollweide projection of Earth, and it has the interesting aspect that all these little ellipses have the same size. However, they are distorted. So you get the same size and density of objects on the night sky, however you pay in terms of distortion if you do this projection. And so what you can do is you can go to the catalog of the brightest stars. This catalog has about 130,000 stars, of course, seen with modern telescopes. And you can ask the question, well, how sensitive is the human eye? So if I take off my glasses, then clearly I'm less sensitive. And even with glasses, I'm less sensitive than my daughter here. So the standard wisdom is we can, in the mathematics or in the astronomy language, see stars up to a magnitude of 6.5. So the scale is inverted, as many scales in astronomy are. So the smaller the number, the brighter the star is. And it goes logarithmically. So another complication that we astronomers love. Anyway, so if you say this is the limit, you see about 8,000 and a bit stars. Typically, other numbers you find is 6,000. So it depends a bit where you put this limit, how you account for, atmospheric problems that, of course, also filter some of the light. So out of this, there are, coming back to our original question, about 58 primary navigational stars, the Polaris star, and many others of the brightest objects. We can just, to orient ourselves, put some of the constellations. So this is Orion that we see on the night sky in winter on the northern hemisphere quite well. This is the Big Dipper that we all know. And if you are further to the south, one of my favorite constellations is Scorpio because it has this beautiful, beautiful shape. So when we talk about the celestial sphere, we have compartmentalized it into little areas, and these areas are the constellations. There are 88, the classical ones, but also new ones. So now if you do that with modern technology, what do we see? So this is another fantastic image because it is not an image. It is an individual star at each pixel. So it contains 1.3 billion individual points with colors as observed with the European astrometric satellite Gaia. So essentially this, you have to go to space because you need to go beyond the shield of the atmosphere on Earth. So you can really pierce into the sky. And if you look away from the sun, you always have a night sky to look at. So if you do that, you can find the positions and the distances and the velocities of hundreds of millions of stars. And if you do that, you notice, maybe I should give you an example of the precision and the beauty of these images. So, but what you see that is there are regions where it appears dark. Also, the colors are faithful reproduction. So, at regions where it turns dark, it also becomes redder. And so, these are really fewer stars that are observed with this satellite. Why are there fewer? Because there's stuff on the light of sight that blocks the light of stars that are further in the background. And so here I have another example. This is the star-forming region of Rho Ophiuchi. And these are really fantastic images that we, of course, not just love or appreciate for aesthetic reasons. We count stars, we look at their distribution, we look at their colors. We can do real physics with that. So when we do that, we get about this schematic picture of the Milky Way. So the sun is roughly here, about 226,000 light years from the galactic center. The galaxy has a bar and it has spiral arms. And we should also notice that the sun rotates around the galactic center roughly once every 200 million years, and it has roughly a speed of 200 kilometers per second. And so the question is, as the star circles around the Milky Way, what is the environment that it encounters, and how does it impact us on Earth? So the first thing I want to do now is I want to zoom into this map. I really want to go back from an artist's impression by really seeing what do we know about the galactic neighborhood. And as we have seen in these dark clouds, I'm not just interested in the distribution of stars, which are roughly homogeneous. I'm more interested in the distribution of gas and dust that blocks stars that lie further behind. So these dense gas clouds are like a shade that you put in front of a lamp, and they block the light of stars in the background. And so if this is our detector, we can count many stars here and very few stars here. And if you know their distance, we can do that in a consecutive step-by-step fashion. And by doing so, we can reconstruct the solar neighborhood and the gas and dust distribution. Before I do that, let's go one step out. Our problem within the galaxy is we are sitting in the very center, no, not in the center, off center, but we are sitting within, and we need to reconstruct things. So it's sometimes good to look at external galaxies and see how they look like. And this is an image from the Fangs collaboration. And what we see in this image is this is obtained with the James Webb Space Telescope. This is an image we obtained in the consortium with the Hubble Space Telescope. And you see the distribution is very different. The stars are relatively evenly distributed, modulo the darkish clouds that block the sun, the starlight. But if you look at the emitting gas, it's now emission of dust, not absorption, as in the previous picture, it is very patchy. It looks like a Swiss cheese. And so, in principle, this could be a role model of our own neighborhood, of the local bubble. So if we do that, we can, let's see, there's a challenge to make this a bit slower. We can reconstruct the gas and dust. We can look at it from different sizes. So the actual local bubble is the blue stuff in the center. This is another image where we add other bubbles and other features. For instance, the red thing is the Redcliffe wave that has been discussed as part of another fellowship a few years ago. And when we do this, we see that our local environment was created by something like 15 to 20 supernova explosions in the last 20 million years. It has a diameter of maybe 1,000 light years. All of the star-forming regions in our neighborhood are associated with the edges of this thing. This has impact because the Earth moves through this. It can squeeze the heliosphere, change the impact of cosmic rays on the Earth's atmosphere, which has been looked at in people here at the CFA. We can then try to ask, because every extragalactic observation goes through this screen of material, how does it impact our view of, let's say, the cosmic microwave background or cosmic inflation, where we try to go to the very edges of the universe? And so in the last minute, let me come back to my question. What are the chances in this context to go from all the stars down to very few stars? And I can place the sun in a simple homogeneous cloud and ask, what are the properties of the cloud, the density of the gas and the size of this cloud in order to retain or lose most of the stars? And so there is a region up here where essentially I'm losing all the night stars. And these are the 2 points I have shown earlier today, before. I can now place the observer onto the map we have reconstructed from the solar neighborhood. Again, there are some key features that we can notice when we look at that in more detail. And we obtain a map like this, and the key aspect is it's essentially yellow. That means because it's like a Swiss cheese, there are so many holes, the chances that you are in a high density region that blocks most of the sunlight is essentially very small. I can do that more quantitatively. I can ask, what is the fraction of stars visible on the wandering Earth? And what is the probability? So if I go here, there is only a probability of, here, 0.1% to lose 40% of the stars. So in most of the cases, most of the stars, certainly enough stars for navigation, are visible. I can do that with a model of the Milky Way that we are producing in Heidelberg, and the situation is very similar. All right, 3 seconds left. What have we learned? The sun, and with it the Earth, is embedded in this tenuous environment, in this local bubble, and it influences much of what we see on the night sky, and it also influences key aspects of us on Earth, like the size of the solar magnetosphere that shields the Earth from cosmic rays. So it has consequences. This environment is, unfortunately, I should say, or maybe fortunately, not rare. It is common to most galaxies. So coming back to the original question, what are the chances that Van Gogh could paint the Starry Night? I think the chances are very high. The probability that the Earth moves into a region of high density that blocks the night sky is very small. And with that, I would like to end.
Thank you, Ralf. That was terrific. And there actually are already some questions on the Slido, so thank you, everybody who did that already. And I have my own questions. Those of you who know me will be amused to know that they're written on this piece of paper, not on the iPad. And so can I poll the audience for you for just a second?
Sure.
So Ralf gave a talk that was part philosophy and part science. And I have a range of questions, some of which are philosophy and some of which are science. So if you want to hear, the 2 choices are more philosophy or more science, okay? So raise your hand for more philosophy. About half the audience, this is not helpful. More science. A little bit fewer, okay. And there's a lot of abstentions, I see, but okay.
I should say makes my life easier because I'm a scientist and not a philosopher. So.
Okay, I'm going to ask Ralf a question that is a personal question, and he may or may not remember this story. So tomorrow, I'm traveling to a castle that the Max Planck Society owns in Germany called the Ringberg Castle, and the astronomers here know what that is. But it's a place where people who are in a similar field gather to talk about a subject for a few days or a week. And about 20 years ago almost, when Ralf was very young and I was younger, we started talking about this, comparing so-called synthetic observations, which Ralf talked about today, with simulations, which Ralf didn't talk about that much, the details of his supercomputer simulations. So let me just say that the idea is you put all the physics you know and all the data you have about some phenomenon into a computer, and you kind of simulate what that would really look like, not in Plato's cave, but outside the cave, in real 3 dimensions. And then what you have to do is actually make observations of it, fake observations, to then statistically compare with real observations. Okay? And at that time, it wasn't quite 20 years ago, but it was a long time ago, I mentioned a particular set of these comparisons, and Ralf said, well, we theorists have no idea, you know, what to even look at. And I remember we said something about ammonia, and you said, why is ammonia a good tracer of dense clouds? And so Ralf has had this huge transformation from somebody who was purely a theorist, purely interested in the real 3-dimensional world, to someone who's really interested in talking to observers and comparing as closely as he can the synthetic observations of these simulations. Hopefully that makes sense to the non-astronomers here. So the question for you, Ralf, is why? What happened in those 20 years that made you want to compare your simulations with real data so much?
So let me start by saying it's interesting to see how other people view oneself. Because
I don't think anyone else was here. I was there at that.
it is often very different to how I conceive my own, let's say.
Do you remember this? It was a discussion of taste testing. Eric Rosolowski and I were torturing.
Yes, I remember there were many. So, but let me answer your question. So I indeed think if you engage in theoretical modeling and it is aloft and only fully embedded in theory space, you can speculate about so many things. And in the end, I at least am interested in trying to understand how nature works and not just some theory space that may or not bear consequences or resonance with reality. And in order to do that, you quickly realize what we have in our theoretical model is very different to what we observe, right? In astronomy, it's a very indirect science. We only can count photons, we only can count neutrinos or gravitational waves. We cannot go to the lab and model a star. We cannot go to a lab and model the dynamics of the universe. In addition, we only typically see snapshots because the time it takes for the Milky Way to rotate once is hundreds of millions of years. We don't have the time to wait for that. There's no way. So we need to always have snapshots, and to interpret these snapshots, we need to make time sequences on a computer in a theoretical model that is as faithful as possible to what we actually see in order to interpret it. And then one approach to do that is, from the observational side, is to gather information for as many different objects as possible so that with statistics you can get a sense of the evolution. With statistics you can get a sense of how to compare things. And so what you need to do is you need to have models that have, let's say, time-dependent chemistry, in my case, modeling the interstellar medium, because we never see the bulk mass itself, hydrogen. We always see trace molecules like carbon monoxide or this ammonia as high density or other molecules, but they are minuscule in terms of mass fraction. And they are chemically changing all the time. So without a chemical network, you may get it completely wrong. You may think, oh, the hydrogen is in atomic form or in ionized form, whereas it may be in molecular form. in the high-density star-forming regions. So all these needs to be taken into account.
And this is perfect, Ralf, because I have to say that the first
Yes.
question that anybody put on Slido was, can you say more about the model types and typical scales, as well as the mathematical, statistical, or computational tools used in your simulations? So a bit of what Ralf just said was an answer to that question, but I don't know whether you want to add more to that, or we should move to philosophy.
So, no, I think it's a proper question that is in the room. It depends a bit on what you are interested in. So if we model the neighborhood of the sun on a computer, we typically have boxes of a few thousand light years. We put as much physics in as possible, self-gravity, turbulence, models of stars and the evolution of stellar feedback, supernova explosions, the radiation. And then we translate these equations, typically partial differential equations, in discretized form into a computer program, and we run that in the national and European supercomputing centers. And we get lots of data, and then the next step is the data analysis. And I can provide more, but maybe we
No, I think I'm going to combine one of my questions with one of these questions. So the verbatim question that one of you asked here is, what do you think the data are telling us about the volume filling fraction of hot gas bubbles in the Milky Way currently? So that's a relatively expert question, which you can answer. But my question that I want to combine it with is, I heard this question about the painting and the Starry Night from Ralf soon after he arrived, and I think what you probably just heard is that Ralf was quite surprised by the answer that he got, that it would look largely the same, even though we're in this bubble called the local bubble, and we're traveling through the galaxy, and in about 5 million years we'll go outside of that local bubble. And the reason is because the details of the observations which Ralf put into his analysis actually show you that things are very patchy. And so theoretically, it might change a lot, but in fact, it doesn't change a lot. And so I'm guessing that you were somewhat surprised by that comparison with the data. And so I guess the question is, what surprises you and what doesn't? And so if you go back to this hot gas bubbles fraction in the Milky Way, do you think the simulations are going to be a good guide, or do we need some special new kinds of observations to do that?
This
is like 5 questions
exactly.
at once, but Ralf can choose whatever part of it he wants.
Let me try to approach the answer. So the first aspect is, if you look backwards, then of course it becomes much clearer and much more obvious than when you start. If you start a process, there are many things you have not...
The process of asking the question.
Yes, and to approach the questions, how to first figure out how can I actually answer this question, right? I mean, you have a question, and then the scientific process is, wow, it's a cool question, but how can I actually answer it? Then you need to figure out what could be a pathway to address this question and come up with something that provides or constitutes a qualitative and quantitative answer. And so I think the volume fraction of this hot tenuous gas is very high, is very, very high, and we see that in the observations. We see that both of the local bubble in the other galaxies. We also see it in the simulations, but many people still think the Milky Way is homogeneous and exponential disk, and I guess some of these thought mindset was still with me when I approached that problem. And so that has changed, but in the hindsight, I think it is quite obvious.
Yeah, and one thing that Ralf said, again, that might not be obvious to the non-astronomers here is he was talking about actual images of other galaxies where we can kind of say maybe the Milky Way is like that, and here's where it looks hot, and here's where it looks not hot. And so that's kind of a third constraint, not just our galaxy and simulations of it, but also other galaxies. So this is related to a sort of almost political, philosophical question that someone asked. Where did it go here? Here it says, you note that at the frontiers of science, everything is uncertain and up to interpretation. Can you talk about the differences in interpretation in the various schools of thought in different institutions and perhaps in different countries? And I'll add in the community of theorists, simulators, and observers as different countries.
Wow, that is a hard question. It is also a question that may have political implications in terms of answer. So I think, yes, there are differences how things are approached, let's say, in Europe and in the US, how things are presented. I think there is maybe a bit more of a salesman aspect here in the US. When I go to conferences, I think that is clearly noticeable. I think it depends very much on the person and the personality who approaches a problem. And maybe I can give a very personal answer. Sure. When I was young, I was struggling with, being heard, or I do all the cool things, but other people are the heroes at the conference, and they would cluster around the big professors and always raise questions and so on. And I try to be similar in some sense, but eventually I realized this is not me. This is not my personality. And once I realized, why should I try to be someone different, a louder person, a more aggressive person? My life was much easier, and it was much more relaxed in these conferences. And surprisingly, your own voice was heard much more. So I think, to me, the key lesson is, and this is also that I give to students and postdocs who ask me a similar question, the key is to be authentic, to be yourself in what you do and how you bring it across to other people and communicate it.
I think that's a fabulous answer. So I'm going to ask you one very factual question and then maybe end with one rather philosophical AI-based discussion. So the very factual question is, do other stars and spiral arms move around the galactic center too? How do we see through the dust lanes?
Okay, so the entire galaxy is rotating. It rotates differentially. So if you go at different radii, they rotate at different speeds, so that a blob of gas that is at one point here gets sheared apart at a later part. Now, from a technical point of view, where the answer gets tricky is that the spiral arms are, in the Milky Way and in many other galaxies, not material arms. Think of a traffic jam on a highway, right? If you go into a traffic jam, you slow down, you with a slow speed go through the traffic jam, and afterwards you accelerate again. And in a sense, the traffic jam moves in the backward direction. And it is exactly the same with the spiral arms. Stars and gas move in, get deflected, change their trajectory, do their thing within the spiral arm, and exit. By the way, similarly, clouds on the sky, right? So this is a very common phenomenon in nature. And so everything moves. So again, back to the Greek philosophers. And maybe we can then come to your Greek or your philosophy question.
Sure. Okay, so it's not completely philosophy, but it's about the future. So there are a lot of questions here. This is, by the way, a tremendous wealth of questions, and I hope somebody's going to give them to Ralf later. So thank you for the great questions. Yeah, I'm going to just skip to this question, okay? Even though, I'm sorry, some of these are terrific. But in terms of the future, because a lot of these are about what is the future of the sun. That's what I was muttering, okay? And Marav Ofer, who was a fellow here recently, has been working with some other people in the audience here, and many of us, to try to think about that. And we can talk about that afterwards. But I don't know, unless you want to say something about what the future of the sun is after it goes out of the local
Depends on what your question is.
All right, let me ask him the hard question and then see what he wants to answer. So I took a picture, Ralf, there's the picture of the 3 apples, one of which was eaten. And Ralf said that AI would have more trouble than humans with that picture. And that's correct. But AI had a surprising difficulty with the picture. It tried to overthink it. Okay, so I'm going to read you. I literally said, "What is in this picture?" Okay, so this is a question about the future of science and what is AI going to do to the future of
you ask ChatGPT,
inquiries
this
like
is
you.
So
That's
cool.
not what I asked. I asked, "What is in this picture?"
Okay.
And it says, "This picture shows a speaker giving a presentation at the Harvard Radcliffe Institute, which is celebrating 25 years of excellence, as noted on the podium sign. The speaker is standing on a stage in a lecture hall with a large screen behind him displaying an image of 3 apples. a red apple, a green apple, and the eaten core of a yellow apple. So 100%. But then it says, the visual metaphor of whole apples progressing to a core may represent concepts like consumption, change over time, or transformation, likely used to support a narrative or argument in the talk. Would you like help interpreting the meaning of this visual metaphor in context? So I said yes, just for fun. And then it said a lot of other stuff that's wrong, that has bold-faced headings about life cycles and evolution and knowledge and truth. And it reminds me of, I'm sorry, I love poetry, but I remember taking poetry classes in college, and people would do all this interpretation of the poetry, and I was like, I wonder if the poet actually meant that. And that's kind of how I feel about this picture. But anyway, I then said, to refine the interpretation, do you know what the talk was about or who the speaker was? And I wrote, that's what it said. And I said, he's saying that AI might have trouble recognizing all of the apples as apples. And then it says, thank you, that makes the metaphor much clearer. In this context, the speaker is using the image to illustrate a limitation or challenge in AI perception and classification. Here's a more precise interpretation. And then it says something astonishingly correct. It says the red apple, green apple, and eaten apple core all belong to the same category conceptually, apple, but they differ significantly in appearance. A human instantly recognizes all three as apples or parts of apples thanks to our ability, to generalize from context, experience, and incomplete information. AI systems relying on visual data may struggle with this because red and green, they basically say what Ralph said. But anyway, it did all this other stuff, and I'm not going to read the rest of it. Okay, but the general idea is it's pretty darn good, better than you might think, but it clearly, at this point, needs some human intervention. Like, no, that's totally wrong, try again. And then it does quite well. But there are people in Ralph's world who are filling in the blanks in simulations with things that AI just generates for the parts that they don't have time to calculate. And so I'm curious, Ralph, what do you think about the value now, 5 years from now, and 20 years from now, and what you might imagine AI doing in an analysis like what you did?
So first of all, I think it is astounding or cool that you picked on a subclause in this huge sequence of things.
It was a good picture.
Yes. So I think AI will be very helpful. We are in a deluge of enormous data amounts. And whereas in the past, astronomy was dealing with individual pictures and, one galaxy, one set of images could be one PhD thesis. Now we have hundreds, thousands, millions of these images that need to be processed quickly. And there is no way we can deal with it without smart image processing, image analysis, and image interpretation, or not just images, data interpretation tools. And AI is one aspect, and I think it will play, and already does play, an important role. So just to close that up, we are trying to use our AI tools that we have developed with colleagues in the mathematics department to bring into the data analysis pipeline of one of the European spectroscopic instruments. And tool does very well.
So I think that there are future reunions of Radcliffe Fellows sometimes, and Radcliffe Day and stuff. So maybe Ralph will come back and answer the questions 5 years from now, 10 years from now, and we'll see what happens. So that was an amazingly thought-provoking presentation. Thank you very much. The questions were extraordinary, and I'm only sorry that I don't have time to ask more because we're already a little bit over time. And so I thank you all. And then I just want to remind you that people, especially who are online, can join other Radcliffe virtual programs, and you can find out about them and also watch videos of this and past events at radcliffe.harvard.edu. And I thank you all for coming and joining online, and I hope you have a terrific day. Thank you.